We will now introduce the Sidenor physics-based model for ladle erosion. This model is designed to answer to Sidenor's pilot challenge in the COGNITWIN project. Sidenor are using steel ladles to transport and to also process the liquid steel. So the ladle is a ceramically lined copper container designed for both treatment and transport of liquid steel. The transport is done by cranes, as you can see in this image. A crane is taking the ladle and lifting it and moving it around depending on what's going to be done with the ladle and the steel inside. The mass of the ladle is typically around 140 ton, but it can be up to 200 tons. And the model we are working on should predict if a ladle can be used safely one more time before relining. It is not a good scenario if steel is leaking out through the side wall of the ladle and actually flowing out on the floor, and it could kill people and create huge problems for and costly damages on equipment. This is a smaller, simplified version of a ladle. So what we see here is a blue area which is steel, and on the side here we see the refractory, and outer part of this is a steel lining or steel shell which is containing the refractory materials. And on the top there is a lid during the refining stage, and there are electrodes coming through the lids which are electrically supplying current through the slag, and by ohmic heating the slag. And when the slag is heated, it will heat the steel. And from the bottom we see bubbles, so there is used different gases, mainly inert gases, to create a bubble plume, which is homogenizing and also doing mixing, but also actually supporting the refining to give good mass transfer in the top surface. So these bubbles will generate not only flow, which goes up in the center, in this case, and down along the walls, but also create surface waves. And these waves are actually also important elements in the erosion of the refractory because of the special motion resulting in large mass transfer coefficients. And we should also mention that there is radiation taking place. So thermal radiation is on the outside to the external, as well as inside the gas phase in the top of the ladle above the metal. So there will be radiation in multiple directions, equalizing the surface temperatures around in the system. Here we look at a detail of the refractory. So to the left we see the region where we have steel or slag flow, which is contacting the first brick. So the bricks with Y1, 2, and 3, these are what we call the wear bricks. These are the bricks that are designed to be eroded, but eroded as slow as possible. And then we have 3 layers of different permanent bricks insulation. Green layer is insulation layer that is close to the outer steel shell. So these layers are supposed to have low conductivity and to protect the steel from being overheated by the hotter inside. So we are actually in the model we have designed, we are using this as a numerical grid for computation of the refractory temperatures, both in the sidewall and in the bottom. So then back to the physics-based model and how it was developed. So the model target is to predict the evolution of temperature and erosion pattern over the lifetime of a ladle. And because of that, the model must be very fast. And the model should be used as a physical-based digital twin, or as an element in a hybrid twin, or in a cognitive twin. So for the hybrid twin, this is about having a model that both exploits the data and also exploits physical laws, conservation laws. And the model should read operational data, which are offline for now, when those are available. And the model should deliver these outer surface temperatures that could be used later to interpret images from thermal cameras to assess internal erosion state, and also, in some cases, the possibility that there's been steel intrusion into the permanent refractory that will cause hotspots at the lower parts of the refractory or outer steel shell. So now the phenomena which we consider are thermal conduction in the both liquid and solid materials, convection by gas purging, the effects of waves, natural convection, the heaters, the slag and metal, refractory, and radiation. And of course, the refractory dissolution itself, and the phase enthalpies of the slag and the metal. These are also important for melting and dissolution, to be able to model this in an appropriate way. And finally, we predict the competition and temperature-dependent solubility of the refractory. So what is not considered here is the erosion due to thermal shocks during the filling of ladle. This is something that can be done by other machine learning approaches and added to the hybrid twin. This slide shows a little bit about how we work with this pragmatism-based modeling or model development, and apply this to the Sidenor pilot in COGNITWIN. So in the upper left, we see the industrial case owners, we have the solution architects, and there is an iteration loop there where the industrial case owners are collaborating with the solution architects, but also using help from the industrial experts to clarify things which are needed. And based on this loop, to have a case definition which can be accepted. If that is clear, what the task is and what we're going to achieve, we start the clarification work of the industrial case to clarify the requirements and to come up with a use case. And there are two loops here. There is one loop to the left, which is about the physics and understanding the physics. And to the right, there is a loop regarding the data, to understand the data. So these things are, in a way, coupled. That to understand the data, you should also understand as much as possible of the physics. So when we have a clear picture here, we can write a model specification, a rather detailed specification, and we can go on with coding of the model. During the writing work, we may actually realize that we do not understand the physics properly, and there will be more iterations to clarify things which are not been addressed earlier. Also, we have another team working with the machine learning methods, and they want to also address this thing with thermomechanical erosion. So they may have their specific requirements, like output, for example, from the physics-based model that they want to have available for their work. So after the model has been coded, it should be optimized and tuned. Inside here, there is also a lot of checking of the model's sanity, if it can do simple conservation tests and be validated against other codes on certain cases. So this is type of unitary testing. And in the first loop, the main loop, if the model can reproduce the data we have got, the model is actually doing a job by itself. But most likely there will be a need from the other machine learning models that are exploiting the data and the model together to come up with a better prediction. And this is in particular important when it comes to the thermomechanical erosion. So we will move to the next slide and talk about tuning of the model to data. So first of all, we need to do these basic checks to check the conservation properties and that the model can do the correct dynamics and that reading and writing of data is done correctly. And when this is done and we have done some decent already first level tuning of the model, we can use the model to check data consistency, because the model is actually doing things exactly the same time, just depending on the input data. So the model is generally much more consistent than the empirical data. So when there are strange results in the empirical data, we may actually use the model to say that, okay, this point should not be used, or we can repair the point if we have sufficient trust in the model and we have validated properly. So then we can do the tuning. All the physical properties should be tuned or are possible to tune, as well as heat and mass transfer coefficients. And of course, there are also other factors like efficiency factors for the electrode and so on that also should be tuned. So then we also have to see that the tuning has physical implications. This is not only an exercise with numbers. Let's say that we need to tune the refractory conductivity dramatically to match the data. What does it mean? Is it possible that this refractory could have that high conductivity? Yeah, it may be possible, because it may be the case that steel has penetrated into the refractory and actually increasing the effective conductivity of the refractory. So that is possible, but then that has huge implications when it comes to the operation, understanding what is going on. So in principle, a physics-based model, if all the coefficients and input data is correct, the model should be able to do a very good estimate of the transients and what is going to happen. We are now going to take a look at the code for the ladle model. In here we have the Python files. Those with starting with test, these are run files, and other files are the source code files. We also can see here that we have a folder called field data. Field data contains all informations from Sidenor when it comes to the operation of the different ladles, and contains time series about how much power was used to keep the steel hot in the ladle, at what times was additions added, different alloy elements or slag formers. And it has information about how much purging gas that was used at different times. This is important to drive the flow and results in different heat transfer coefficients and erosion patterns as well. And if you want to run the model, we can open a typical run file, which is called test3. And in this file, we have different informations that we have to give, like, for example, the year we are looking at. So we have complete data for a few years, and here we're looking at 2019. So we are reading a file called process parameters, and we also have other data which is read based on this file. Here we can give the ladle number. So this year the Sidenor was operating with a given number of ladle numbers. So it was not 16 ladles, but numbers start at 1 and the highest number is 16. Right now we can select to look at ladle number 4. So with this setting we will run all the cases that belongs to ladle number 4 during 2019. And this will also write different informations to the file and produce also images from the plots. So let's run the test 4 or ladle 4. So then we use Python 3. And what's happening now, we are reading in the data, the industrial data, and the numbers here are the ladle ID. These are the unique IDs that identifies one specific ladle and one specific use of that. So all ladles or all uses have their unique IDs. And we can see now that already the code has been running, say, eight uses of that ladle, starting at the beginning of 2019. And there's quite big number of uses during 1 year. So typically one use will take like 4 hours from metal was filled into it from the electric arc furnace until the ladle will come back for another use. So we have to simulate the temperature of the refractory and also of the steel during the time there is processing of steel inside the ladle. And after that we simulate the temperature of the refractory to have that as input for another model to assess thermal degradation of the refractory. So we will now take a look at what happened on the different folders we have produced here. So this was not a good place to start. Okay, so we haven't just taken over again over the folders. So we have one folder here called plot. So when we run the model in this mode we have seen now, we save information on this plot folder. So we will go there, and we will see that there is created a huge number of subfolders, but also some local plots. But we are focusing on the subfolders. And when it comes to ladle 4, we have three different folders created here: 4_0 to _4. So actually 5 folders. So we go to the first one. And if you look at the contents here, we have a lot of PNG files. These files will actually have the temperature and the power used by the heating electrodes to keep the metal warm. So these plots we can have a look at later. But now we will just look at the output file that is produced here. That is this file, max erosion ladle. And we are opening this file now in LibreOffice Calc. And we can look at the numbers which are in this file. So here we see this is ladle number 4 as we put into the input file, the different heats for the ladle. So this is actually one lifetime of the ladle. So we can see that in this case, it looks like the ladle was not lasting very long before it was worn out for some reason. We have the unique IDs. We have the maximum eroded fractions of the wear bricks. So when this number approaches 0.75, the ladle is not safe to use anymore, according to the rule set by the company, the steel company, Sidenor. So we can see here that these numbers are after some 51 uses, we are hitting the 75% limit. And at that stage, the ladle will be repaired. But only the lower part of the ladle is repaired. The upper part is repaired. The lower part is not repaired because erosion is generally smaller in the lower part. So in the model, when we are coming to this point, we are actually making a numerical repair. We are repairing the same bricks as done in real operation, and we are continuing calculations. So we can see here that most likely we are predicted the time of repair somewhat too late, and also we are not entering a maximum erosion when the ladle is taken out of use for demolition of the refractory. This we have not looked into very much yet. We are focusing on understanding the temperature and how this is input to the general model. This column shows average erosion. That is much smaller than the maximum erosion. So for the safety issue is coupled to the maximum erosion for sure. This column is about the waiting time. So the waiting time is the time between the ladle was emptied for metal and until it's used again next time. So we see that the waiting times vary a lot from around maybe 1 hour. There is one number here which is 1, which looks very unrealistic, but this is the data we have. So it looks like in this case there are things to inspect more closely in the data. We also see that there are points here when waiting times are quite long. So these are several hours, 1200 minutes. The temperatures that we see are the temperatures the ladle have after the waiting time, when it's receiving new metal from the electric arc furnace. And these temperatures are important for thermal degradation, because if the ladle is cold and the metal is always well above 1600 centigrades, there will be quite some thermal or thermomechanical erosion when the hot metal hits the bricks in the ladle or get in contact with the bricks. So these numbers are important numbers for making an assessment of this thermomechanical contribution to ladle erosion. But it's also important for the more classical mass transfer controlled erosion, because the temperature of the wall and the steel impacts solubilities and different kinetical contributions to the mass transfer and, and the refractory dissolution. Here we have the steel mass in tons. The steel mass is basically a part of the operational data, but now it turns out that the steel mass is not the steel that is in the ladle, but that is the steel that was received by the casting machines. And sometimes there are problems in the casting machine. So we had to make some corrections because sometimes the cast metal was very low, so we have put a limit here of 110 tons. So if the cast metal was less than 110, this is deemed unrealistic, and we set a lower limit for the metal in the ladle. The metal in the ladle actually is quite important because when you heat the metal, if you have a small amount of steel in the ladle, you will get a very solid heating effect if you have half the amount of steel than you normally would have. So then this is important corrections. In this column we can see if we have temperatures from the electric arc furnace. If we have measured temperatures at this point, we can use this to estimate the first temperature of the steel in the ladle. And this is needed by the model because our model will have to start with some temperature. And now it turns out that the first measured temperature in the operation is actually not a measured temperature. That is a temperature that was sitting in the system from the previous use of previous operation in the refining station. So that typically that will come from not from the same ladle, but from a previous from another ladle on the having the ID before this actual run. So, for example, this first run here, the first temperature that is logged the system is actually not real, but coming from the ID number 203245. Anyway, we are computing different residuals based on this and the data which is deemed to be valid. So we have a residual that just computes the level of the temperatures predicted versus the measured. And we have another residual which is an RMS residual. So if the level is correct, the residual 0 will become 0, but the shape of the curve will be still controlled by the residual 1. So we can use this residual to deem which actually set of parameters in the model are fitting best with the data. So the results can also be visualized, and we will look into that in a separate video. We are using ParaView for visualization of the results. And we also have model tuning. And to give you some idea about that, I'll go back here. And we have test 4 is a new file. And we can run single IDs or we can run multiple IDs. Right now we see an case where we're doing is picking one specific case, and we can put in a vector of different tuning parameters. This is for the conductivity of the magnesium, oxygen, carbon inner refractory. And here we have different refractory elements. The steel shell we don't want to tune because that is pretty accurate data we have. This is a thermal heat transfer coefficient. This is the efficiency of the heating electrodes, because some heat will be lost to the outside by cooling water or by radiation, so it will not never be 100%. And we have emissivities of the outer wall of the ladle, and also internal between the slag and the refractory, and the lid inside the ladle. So these are our parameters, but we also have a number of other parameters that we can vary to do the tuning. So as a result of running this we get the file which is giving us the different parameter values, and we have the residuals. And it's of course for a simple file very easy to inspect which parameters which have the larger impact on the residuals, and we can also do processing of this data to find gradients and to find out where we should go to focus the center of the tuning. So typically we will like to use some methods like fractional designs, factorial designs for doing this. But to do that, we need to have a very good idea about where we should have our center point. So this is a sort of iterative process. But at the end, we can run all the cases and see if we can actually find a tuning, a set of tuning parameters that can be used for all the cases. Now we know that two ladles are not exactly the same, because they are not. You can copy those exactly when you're doing the bricklaying and all the things that is needed. So it will be. This is not exact, but this is as close as it is possible to get. We will now take a look at the results, which ends up in the plot folder. Here we have results from a huge number of different runs, different ladle numbers. The one we were running was ladle 4, and ladle 4 we will have down here. So this is plots from this run, and we will open the plots and just have a look what's there. So what we see now is a plot from ID 203246, and the numbers on the top here are basically the two large numbers are the most important. These are the residuals based on the temperatures. So we can now see that in this plot we have time of roughly 2 hours, not fully 1.5 hours. We have temperatures in centigrades, and the yellow line are the measured temperatures, measured with the thermocouple and a sort of mechanical sampling device. And the blue is prediction by our model, and the red curve is the energy that is added to the steel. So in the periods where the curve is ramping up rapidly, the electrode power is on, and then the power is off in these periods when the curve is flat. So what you see here is that the first temperatures are not matching, and that's because the first point in the measurements are actually not a real measurement. That's something that sits in the system from the previous operation. So this belongs to another ID basically and cannot be used, but we are using the other points except the last point. So the second until the next last point are used to compute the residuals. So we see here that residuals are doing quite well. We are a little bit lower on the average on the temperature, but this is a rather good comparison. We can also see that when we are injecting additions to the ladle, this can be alloying elements or slag formers, the temperature in the model is dropping down. And so this happens at 3 different times. And these details are, of course, not captured up by the measurement, which are done just at a few times. If you now just flip through a number of these results, you can see here that in this case the comparison is not as good, mainly because the start temperature seems to be off, and that is not we don't have a measurement for the start temperature. So again, we see that the shape of the curves are pretty good. But there is some room for improvement by working more with the tuning. But this one is very, very good. And we can see that this is a special case where there is clearly something wrong with the way the power has been plotted. So we have a huge number of these results. So they are useful for inspection, to see what's going on, to get a more hands-on view about the consequences of tuning, and if we can capture the correct trends in the ladle when it comes to temperature. So the steel temperature is the measured one, not the temperature in the refractory, which we are simulating, but we are simulating both. And we use the steel temperature as a measure on the refractory temperature. So if the model can reproduce the steel temperature, how it varies, it should also be quite good to reproduce the temperatures in the refractory, in the bricks. So I'll just flip through this to the end, and we see that there's a lot of cases. Some are good, some are less good. So if you go back a few, we can maybe take one. Clearly, this is a result again of the start temperature in the simulations. So we will end this here. We will now take a look at the data from the ladle model after being read into ParaView. So here we see a slab of the side of the refractory. We see erosion patterns, and this pattern that we see here, this is the inner part of the refractory. So the inner bricks are eroded, and this strange pattern is a result of the repair. So the ladle was repaired above this position earlier, and after the repair, the ladle is being still worn more below the repair point, but also above repair point. So this is producing this little bit strange profile. And we can have a look at how the temperatures evolve if you're looking at the transient. So we see here that the temperatures in the refractory at the time just before filling the metal into the ladle is a result of the history of this refractory, how long time since it was last used, and also how long time it has been passing since last use until the next use. So if we run this video, we see that when the metal is being filled into the ladle, it heats up very fast. In the lower part, it heats up by contact with the hot steel, and the upper part due to redistribution of energy by radiation. And we can also have a look at the outer wall temperature. We can limit the temperatures here, so we can maybe scale it down to 650. to 800. So if you now run the visualization, you see that the temperatures are actually initially somewhat lower at the point where the refractory is thin. This is because it is easier to drain out the energy during waiting time at these points where you have less stored energy. You also see that there is some gradient in the temperature. So it's slightly cooler at the lower part and slightly hotter at the point where we have heavy erosion. So right now, temperature calculations indicate that at points which are thin, we should expect somewhat slightly higher temperatures. And this information could be used in conjunction with thermal cameras to say something about the state of the refractory. So we will now go into a summary slide. We have seen that we have developed a model which now can predict quantitatively the temperature in the steel and the refractory. And of course, we also predict the slag temperature, but we cannot validate it because we have no information. So we can only validate the steel temperature in this case. The model also predicts refractory erosion and the erosion pattern. This is not tuned yet to the data. That is remaining work. We have developed a fundamentally based enthalpy model to handle the melting and dissolution. This was implemented and is used for handling, in particular, the addition of slag former and other alloying materials into the ladle. We have a refractory erosion model which is based on chemical dissolution of the refractory, dissolving elements into the slag or into the steel phase. And we also developed a tuning strategy exploiting all the data. The computational speed of the model must be fast. So we have in earlier found that we can run typically a couple of hours real time in roughly 2 seconds. So this is important for be able to use all the data in any sort of tuning operation. Of course, we can do this, run multiple processors to do this. That's also an option to be considered. So the model will now be combined with data-based ML AI methods, and this applies in particular to the thermomechanical contributions to erosion. We're also looking into introducing cognition elements, and the main thing here will be to combine the operator's experience with model predictions, and by merging this to have one solid prediction of if the ladle is in sufficiently good condition to have one more safe use, or it should be repaired or demolished. This was all for now. Thank you.